In the summer of 1950, in northern New Mexico, 4 men walked from the technical area of the Los Alamos National Laboratory to a cafeteria in a log and stone building called Fuller Lodge to have lunch. Their names were Emil Konopinski, Edward Teller, Herbert York, and Enrico Fermi. They were, all 4 of them, physicists, men who had built, in that same complex of low buildings, the atomic bomb, and who were then engaged in building its more powerful successor. Fermi was Italian by birth, 49 years old, and had been given a Nobel Prize 12 years earlier for his work on induced radioactivity. He was known, among the physicists of his generation, for 2 things. The first was the extraordinary breadth of his physical intuition. He could, in a moment of pausing, calculate almost any quantity in physics to within an order of magnitude on the back of an envelope and be roughly right. The second was that he was a man of very good humor. He liked to walk. He liked to talk. He liked in particular to ask questions. On this particular walk to lunch, on this particular summer day, the conversation had wandered, as physicists' conversations often do, through the trivial and into the extraordinary. In the previous few weeks, the newspapers in the American Southwest had carried a rash of stories about unidentified flying objects. And more curiously, that spring in New York City, the sanitation department had reported an inexplicable increase in the theft of public trash cans. The cartoonist Alan Dunn had put these 2 things together in a cartoon in the New Yorker magazine of the 20th of May of that year. A single panel drawing, without caption, of little green humanoids in a flying saucer, unloading New York City trash cans from their own craft into the saucer's hold. It was the kind of cartoon that made the reader smile without quite knowing why. And then, later, wonder why the smile had faded. The 4 physicists had discussed the cartoon. They had discussed, generally, the interest of the moment in flying saucers. They had discussed, with the seriousness of men to whom the phrase interstellar travel was a set of engineering problems rather than a piece of fiction, the plausibility of a civilization ever crossing the enormous distances between the stars. They arrived at the cafeteria. They sat down. They began to eat, and in the middle of the meal, into a conversation that had by now moved on to other things, Fermi looked up and said, "But where is everybody?" The 3 other men, according to Herbert York, needed no clarification. They knew immediately what he meant. He had done the calculation in his head. He had estimated the number of stars in the Milky Way galaxy. He had estimated the fraction of those stars that ought to have planets, and the fraction of those planets that ought to have the conditions for life, and the fraction of that life that ought to have gone on to develop technology. He had estimated the speed at which such a technological civilization, once emerged, could plausibly spread itself from star to star. And he had noticed that the number of stars in the galaxy is enormous, that the galaxy is very old, and that even at a modest fraction of the speed of light, a determined civilization could visit every star in the Milky Way in what is, cosmologically speaking, a very short time. Perhaps 10 million years, perhaps 100 million, in a galaxy that is 13 billion years old. If any of this had happened, if any of the tens of billions of sun-like stars, some of them born 9 or 10 billion years before ours, had produced a civilization that had gone on to explore the galaxy, then that civilization, or its descendants, or its self-replicating machines, or its radio signals, or its garbage should already be here, all around us, unmissable. And yet, when Fermi looked up from his lunch and asked the question, nothing was here. The sky was empty. The radios were silent. The trash cans, whatever the cartoonist thought, were being stolen by ordinary human beings. Where, he asked his lunch companions, is everybody? Fermi died 4 years later, in 1954. He never wrote the question down. He never published on it. The 3 physicists who had been at that lunch remembered it over the years and told the story in slightly different ways to slightly different people. Teller remembered Fermi saying, quite unexpectedly, "Where is everybody?" Konopinski remembered him saying, "But where is everybody?" York remembered a longer version, "Don't you ever wonder where everybody is?" And remembered Fermi following it, immediately, with a burst of numerical estimates. The question, as Fermi asked it, was a small moment in a lunch conversation. It did not become a paradox in the formal sense until much later. In the June of 1975, 25 years after that Los Alamos lunch, a young American astrophysicist named Michael Hart, working then at the National Center for Atmospheric Research in Boulder, Colorado, published a paper in the Quarterly Journal of the Royal Astronomical Society. It was called, plainly, An Explanation for the Absence of Extraterrestrials on Earth. Hart's paper opened with what he called Fact A. Fact A was this: there are no intelligent beings from outer space on Earth now. He went on to argue that this fact required an explanation. If interstellar travel were physically possible, and if intelligent civilizations arose with any regularity anywhere in the galaxy, then over the age of the galaxy, at least one of them ought to have done what humans would probably do, given the time: spread outward from its home star in slow waves until every corner of the Milky Way had been at least visited and perhaps colonized. Hart calculated the time such a wave of colonization would take. Even at 1/10 of the speed of light, he found, a speed we might, ourselves, one day reach, the Milky Way could be crossed in around 650,000 years. Upper limit, 2 million. 2 million years is, in the age of the universe, essentially nothing. It is less than the age of our own genus. The galaxy has been available for colonization for something like 10 billion years. If any civilization, anywhere in it, had ever set out, we should be neighbors by now. We are not neighbors, not with anyone. 5 years after Hart, in 1980, another physicist, Frank Tipler, extended the argument. Tipler pointed out that if a civilization is even modestly good at engineering, it does not need to send ships full of colonists to every star. It only needs to send one probe capable of building a copy of itself out of the materials available at its destination. 2 probes, then 4, then 8, then 16. A self-replicating expansion out from the parent star, spreading with only the speed of physical travel to slow it down. The Milky Way could be filled with such probes, Tipler calculated, in perhaps 300 million years. Again, in cosmological terms, essentially nothing. And so, the question that Fermi had asked at lunch, in an offhand way, became a formal problem. It became known as the Fermi Paradox, a name Fermi himself had never heard. first attached to his lunchtime question in print in 1977, 3 years after Hart's paper. The paradox is this: the galaxy is large, and it is old. The conditions for life are, so far as we can tell, not exotic. The tools of interstellar travel and communication are not, as far as we understand them, physically forbidden. And yet, when we look up, we see nothing. When we listen, we hear nothing. The universe has, so far, said nothing to us. And in the 60-odd years since Fermi's lunch, we have spent a great deal of effort trying to understand what that silence means. To feel the shape of the paradox, you have to feel the shape of the numbers. Our galaxy, the Milky Way, contains between 100 billion and 400 billion stars. Recent estimates from the European Space Agency's Gaia mission cluster around 200 billion. This is a difficult number to hold in the mind. If you were to try to look at each of those stars in turn for 1 second per star, without pausing to sleep or to eat, it would take you more than 6,000 years to reach the end of the list. Our galaxy is not a small one, but it is not the largest. It is one of 2 or 3 trillion galaxies in the observable universe, the sphere of space from which light has had time to reach us since the beginning of everything. If you multiplied the number of stars in the Milky Way by the number of galaxies, the result would be a number so large that human intuition, honestly, refuses to hold it. But we do not need to worry tonight about the whole universe. We can restrict ourselves to our own galaxy, to the 200 billion stars closest to us in any meaningful sense. And the paradox is already sharp enough. The Milky Way is old. The oldest stars in it are around 13.5 billion years old. Our own star, the Sun, is about 4.5 billion. That means there are stars in our own galaxy, which, when the Earth was only just condensing out of the accretion disk around the young Sun, had already been shining for 8 billion years. Any planets around those stars, and there is no reason to think there aren't some, have had 8 billion additional years compared to Earth to do whatever it is that planets do. Earth, in those 4.5 billion years, has produced a great deal. The first evidence of life is around 3.7 billion years ago. Microbes in ancient rock. The first eukaryotic cells, the ancestors of every plant and animal, around 2 billion years ago. The first complex multicellular animals in the Cambrian explosion, only 538 million years ago. Our own genus, Homo, around 2.5 million years ago. Anatomically modern humans, the same species that is watching this now, around 300,000 years ago. The first radio transmission was in 1895. That is 130 years ago. If Earth's 4.5 billion years were compressed into a single calendar year, humans would appear in the last 30 seconds of the last day of December. Radio would appear in the last 100th of the last second. In 1961, in a small conference at the National Radio Astronomy Observatory in Greenbank, West Virginia, a young astronomer named Frank Drake proposed a way to think about the numbers. He wrote it as an equation. The equation, later called the Drake equation, is a chain of factors, multiplied together, which try to estimate the number of civilizations in our galaxy right now that are technologically capable of communicating across interstellar distances. The first factor is the rate at which new stars form in the Milky Way. We know this reasonably well, a few solar masses per year. The second factor is the fraction of those stars that have planets. In 1961, this was a guess. Today, thanks to the Kepler Space Telescope and its successor, TESS, we know it is essentially all of them. Almost every star, when we look, has planets. The third factor is the average number of those planets that are, per star, potentially habitable. The number of Earth-sized worlds in the temperate zone where liquid water can exist on the surface. This is one of the great numerical questions of contemporary astronomy. Different analyses of the Kepler data give different answers, from around 2% up to around 60% for Sun-like stars. A safe middle estimate is that somewhere between 10 and 30% of Sun-like stars have such a planet. If you take even the low end, 10%, and multiply by the 200 billion stars in our galaxy, and by the fraction of those stars which are Sun-like enough to be interesting, you arrive at a number of potentially habitable, Earth-sized temperate worlds in the Milky Way that is, at minimum, in the low billions. Billions of Earths in one galaxy, not counting the trillions of galaxies beyond. The remaining factors of the Drake equation, the fraction of habitable planets on which life actually arises, the fraction of that life which becomes intelligent, the fraction of intelligent life which becomes technological, the fraction of technological civilizations which are actively communicating right now, and the average length of time a civilization stays in a communicating state. None of these, 60 years after Drake wrote them down, are known. They are guesses, educated guesses, thoughtful guesses, but guesses. Depending on which numbers you plug in, the equation returns anywhere from millions of communicating civilizations right now in our galaxy to less than one, which is to say, ourselves alone. The equation, in this sense, is not really an equation. It is a scaffolding for thinking about our own ignorance. It tells us what we would need to know in order to know how alone we are. The other number worth holding before we move on is the distance. The nearest star to the Sun, other than the Sun itself, is a small red dwarf called Proxima Centauri. It is 4¼ light years away. That means that a beam of light, traveling at the fastest speed anything can travel in this universe, takes 4¼ years to cross the gap between us and the next star out. The Voyager 1 spacecraft, launched by the United States in 1977, is the fastest object humans have ever sent into interstellar space. It is currently traveling at 17 kilometers per second. If it were pointed at Proxima Centauri, it is not. It would take around 73,000 years to arrive. The Milky Way is roughly 100,000 light years across. At Voyager's speed, crossing it would take 1.7 billion years. At 1/10 of the speed of light, a speed we do not know how to achieve, but which does not appear to violate the laws of physics, the crossing would take 1 million years. At the same speed, the whole disk of the galaxy could be visited, with reasonable pauses at each star, in perhaps 10 million years. 10 million years is 1/300th of the age of the galaxy. If any civilization, at any point in the last several billion years, had wanted to fill this galaxy, they had time. The first serious attempt by humans to hear another civilization began, quietly, in the spring of 1960. Frank Drake, the same Drake who would later write the equation, was a young radio astronomer at the National Radio Astronomy Observatory at Green Bank in the Allegheny Mountains of West Virginia. He had access, for a few weeks, to a 26-meter radio dish called the TESS telescope, and he decided, without much fanfare, he did not tell his superiors what he was really doing until the project was well underway, to point that dish at two nearby sun-like stars and listen. The stars were Tau Ceti, 12 light-years away, and Epsilon Eridani, 10.5. Drake tuned the receiver to a specific frequency, 21 centimeters in wavelength, 1,420 megahertz, the natural emission frequency of neutral hydrogen. Any civilization, Drake reasoned, that had begun to study the universe would sooner or later notice that this was the loudest natural signal in the galaxy, and would think of it as a plausible carrier frequency for interstellar communication. 2,000 hours of dish time spread over a spring. The project was called Project Ozma, after the queen of the imaginary land of Oz. Ozma detected nothing. 14 years later, on the 16th of November, 1974, at the dedication ceremony of an upgraded receiver at the Arecibo radio telescope in the mountains of Puerto Rico, Frank Drake, with input from Carl Sagan, did the opposite. He transmitted. The transmission was a binary message, 1,679 bits long. When arranged in a rectangle of 23 by 73 pixels, it produced a simple image, the numbers 1 through 10 in binary, the atomic numbers of the elements that make up DNA, the double helix, a stick figure of a human, with an estimate of the human population of Earth in 1974, the layout of our solar system, and a diagram of the Arecibo dish itself. The message was aimed at a globular cluster called M13, a dense ball of several 100,000-old stars in the constellation Hercules, 25,000 light-years away. If any of those stars have anyone listening, and if any of them chose to reply, the answer will arrive in the year 51,974, give or take, in the calendar we would still by then be using. The Arecibo message was, in its way, a gesture rather than a serious attempt at communication. Drake and Sagan knew this, but it was the first, and remains one of the very few deliberate messages ever sent from Earth in the hope of being heard by someone. The dish that sent it collapsed on the 1st of December, 2020, in a slow structural failure. The Arecibo telescope no longer exists. The message continues on its way through the galaxy, at the speed of light. It is now about 51 light-years out. It has crossed a small handful of stars. There has been, so far, no reply. 3 years after the Arecibo message went out, on the 15th of August 1977, at around 11 at night, local Ohio time, a volunteer astronomer named Jerry Amon was reviewing the previous evening's data from a radio telescope called Big Ear at Ohio State University. Big Ear was doing what most radio telescopes do most of the time, surveying the sky, one narrow strip at a time, recording the intensity of radio emission at each point on a printout. The printout was in the form of columns of numbers and letters, with each character representing the signal strength for a small patch of sky. Most of the sky, on most nights, is quiet. Most of the characters were the number 0 or the number 1, background noise. At around 10:30 in the evening of the 15th, coming from a point in the constellation Sagittarius, the Big Ear had recorded a burst of narrowband radio emission that lasted for 72 seconds, the exact time it would take a fixed point in the sky to pass through the telescope's field of view. The intensity, at its peak, was more than 30 times the background noise. It was on the 21-centimeter hydrogen line, the frequency Drake had listened at 17 years earlier. Eamon, reviewing the printout, saw the string of characters. He circled them in red pen. In the margin, he wrote, in the same red pen, a single word. Wow. The signal has never been observed again. For nearly 50 years, radio astronomers have pointed telescopes back at that patch of sky, at that frequency, and heard nothing. Explanations have been offered that it was a passing comet outgassing hydrogen, that it was a piece of orbital debris, that it was Earth-based interference. Each of these has been carefully investigated. None of them, so far, has withstood scrutiny. The wow signal remains, the single most compelling and the single most unrepeatable, unexplained radio event in the history of the search for other civilizations. Since Big Ear, the listening has become organized and international and, as much as anything of this kind can be, funded. In 1984, the SETI Institute was established in Mountain View, California, a private non-profit dedicated, among other things, to the search for extraterrestrial intelligence. Through the 1990s and 2000s, it ran a project called Phoenix, which observed around 800 nearby sun-like stars for signals at hundreds of channels each. Phoenix found nothing. In 2015, the Russian-American venture capitalist Yuri Milner, working with Stephen Hawking, announced a program called Breakthrough Listen, a 10-year, $100 million commitment to the most sensitive, most systematic search for radio signals from other civilizations that had ever been attempted. Breakthrough Listen uses the largest radio telescopes on Earth, the Green Bank Telescope in West Virginia, the Parkes Dish in Australia, the Meerkat Array in South Africa. It listens across billions of channels, at millisecond resolution, at multiple frequencies simultaneously. It has been running now for a decade. It has produced, to date, no confirmed signal from any other civilization. There have been candidates. In 2019, Breakthrough Listen recorded, from the direction of Proxima Centauri, our nearest neighboring star, a narrowband tone at 982 MHz, with the sort of Doppler drift that a signal from a planet in orbit ought to have. It was called BLC-1. It was, for a year or so, the most exciting candidate the search had ever produced. By the autumn of 2021, two independent teams of astronomers had shown, to a high degree of confidence, that BLC-1 was not a signal from Proxima Centauri. It was an artifact, an intermodulation product of two different Earth-based transmitters, most likely oscillators in nearby electronic equipment, whose harmonics happened to Doppler drift in the same direction as the telescope's pointing correction, over the same length of time. It was our own signal, reflected back to us in the noise. This has been the pattern. Every candidate, in the end, has resolved itself into something local. The universe has not spoken. It has, so far, only reflected us. There is one honest caveat. In 2018, three astronomers, Jason Wright, Shubham Kanodia, and Jeffrey Luber, published a paper called How Much SETI Has Been Done. They calculated the total volume of the space of possible searches, a space that has many dimensions: frequency, sensitivity, direction on the sky, time observed, modulation, polarization, and so on. They calculated the fraction of that space, which humans in 60 years of listening have actually searched. The fraction they arrived at was around 5 parts in 10 to the 18th, which is to say, essentially nothing. They offered, in the paper, an analogy. If the total space of possible searches were represented by the volume of Earth's oceans, then the volume that humanity has, so far, actually listened to, is roughly the volume of one hot tub. We have listened to one hot tub of the ocean and found no fish, which is not, when you put it that way, quite so alarming. There is no shortage of proposed answers to Fermi's question. Since Michael Hart's paper in 1975, physicists, astronomers, biologists, and philosophers have written, between them, hundreds of possible explanations for the silence. Most of these explanations fall into one of a few families. It is worth, tonight, walking through the main ones. Slowly, in no particular order, without trying to decide between them. Some of them contradict each other. Some of them are complementary. Some of them are, at this point in our understanding, indistinguishable from one another. All of them, taken together, form what might be called the modern catalogue of loneliness. The first family, and the largest, is the family called the Great Filter. In an essay published on the internet in 1996 and expanded in 1998, the American economist and futurist Robin Hanson proposed that somewhere between the raw ingredients of a lifeless universe and a galaxy-spanning civilization, there must be at least one enormously improbable step, a step so unlikely that, on average, it happens only once in every 10 billion planet years, or once in every trillion, or once in the entire history of a galaxy. This step, whatever it is, filters out the great majority of would-be civilizations before they get to the stage of visibly colonizing space. The interesting question, Hansen pointed out, is where this filter sits. Is it behind us, or is it in front of us? If the filter is behind us, then the improbable step has already been passed. Perhaps abiogenesis, the arising of life from non-life, is very rare, and Earth is one of the extraordinarily few worlds where it happened. Perhaps the arising of eukaryotic cells from simpler ones, an event that seems to have happened only once on Earth in 4 billion years, is the bottleneck. Perhaps intelligence itself is exceedingly rare. In any of these cases, humanity is on the far side of the filter, and the universe is quiet because it is empty. If the filter is ahead of us, then the improbable step has not yet occurred, and it will occur, for us, in our future. Perhaps every technological civilization, given enough time, destroys itself by nuclear war, or by engineered pandemic, or by artificial intelligence, or by ecological collapse, or by some catastrophe we cannot yet imagine. In this case, the silence of the galaxy is a warning. The philosopher Nick Bostrom has argued that the discovery of independent microbial life anywhere else in the solar system, on Mars, in Europa's ocean, in the plumes of Enceladus, would be, on balance, terrible news. It would suggest that the filter is not behind us at the origin of life, which would suggest, by process of elimination, that some later step, possibly the one we have not yet reached, is where the great narrowing happens. The great filter is not really an answer. It is a shape into which answers can be poured. But it is a useful shape, and it has been influential. The second family is called rare earth. In 2000, two American scientists, Peter Ward, a paleontologist, and Donald Brownlee, an astronomer, published a book called Rare Earth, which argued that microbial life is probably common in the universe, but that complex animal life, of the kind that could ever build a radio, is probably not. Their argument is a long list of the things that had to be or not be for Earth to work. Our star had to be a certain size, massive enough to be stable for billions of years, but not so massive it would burn out before life could evolve. We had to be in a certain zone of the galaxy, metal-rich enough to have rocky planets, but not so close to the crowded galactic center that we would be sterilized every few million years by nearby supernovae. We had to have a Jupiter at a certain distance to sweep the inner solar system clear of the worst of the incoming comets and asteroids. We had to have a moon of a certain size to stabilize the tilt of our axis over billions of years, without which our climate would swing wildly and complex life would not have the stability it needs. We had to have plate tectonics to recycle carbon and to build continents. We had to have oceans. We had to have the right kind of magnetic field. We had to have a very particular history of catastrophic events, including at least one event, 66 million years ago, that killed the dinosaurs and allowed the mammals to inherit the planet. Ward and Brownlee did not argue that any single one of these conditions is impossibly rare. They argued that all of them together, occurring on the same planet, may be rare enough that Earth is essentially unique in the galaxy, or at least so rare that our nearest complex life neighbor is thousands or millions of light years away, effectively out of reach. Rare Earth is a version of the Great Filter, with the filter placed at a very specific step, not the origin of life, but the origin of animals. The third family, and one of the more recent, is called the Dark Forest. In 2008, the Chinese novelist Liu Cixin published a novel called The Dark Forest, the second book in a trilogy about first contact between humanity and an alien civilization. In the novel, Liu proposes what has come to be called the Dark Forest hypothesis. It runs like this. Any civilization has, as its primary interest, its own survival. Any civilization, over time, tends to grow in population, in energy demand, in reach, in a universe where matter and energy are finite, and where any two civilizations occupy different points in space and time. Any given civilization cannot know, from its own vantage point, whether another civilization is peaceful or hostile. It also cannot know how quickly another civilization is developing. The other civilization may currently be less advanced, but may, in the time it takes a signal to be exchanged, become far more advanced. And a sufficiently advanced civilization, at interstellar distances, can plausibly destroy a less advanced one without warning, without cost, and without much risk to itself. Under these conditions, Liu argued, the safest strategy for any civilization is to remain silent and to eliminate any other civilization that reveals itself. The galaxy, in this picture, is a dark forest. Every branch that snaps is a hunter giving away their position. The wise, therefore, do not snap branches. They listen, they watch, they stay very still. If Liu is right, then the silence of the sky is not the absence of civilizations. It is their strategy. The fourth family is quieter. It is the zoo hypothesis. In 1973, an American radio astronomer named John Ball, working at MIT, proposed that the reason we do not hear from anyone is that the older civilizations of the galaxy have collectively decided, for reasons of ethics or of science, to let us alone. We are, in his phrasing, a reserve, the way certain areas of the American continents were, in a different context, set aside from human settlement. The old civilizations are aware of us. They are watching us. But they have chosen not to reveal themselves, because the value of an undisturbed emergence is greater than the value of contact. This is a very old story, in fact. The Russian rocket pioneer, Konstantin Tsiolkovsky, in an unpublished essay from 1933, had made almost the same argument 40 years earlier. The zoo hypothesis is difficult to test. That is, in a sense, its point. If the older civilizations have decided not to reveal themselves, then the absence of any revealing is exactly what we should observe. It is the answer that makes no prediction, which is not, in science, an easy sort of answer to hold. But it is not, on its face, wrong. The fifth family is called aestivation. In 2017, 3 researchers at the Future of Humanity Institute at Oxford, Anders Sandberg, Stuart Armstrong, and Milan Cherkovich, published a paper with a strange proposal. They pointed out that any advanced civilization, if what it is doing with its intelligence is fundamentally computation, thought, simulation, exploration of possibility, has an incentive to do that computation as efficiently as possible. And there is a physical law called Landauer's principle, which says that computation is enormously cheaper at lower temperatures. The current temperature of the universe, the background temperature of empty space, is around 2.7 degrees above absolute zero. It is very cold. But it is, in cosmological terms, still hot. In some tens or hundreds of billions of years, as the universe expands and cools, that temperature will fall much further, and at those lower temperatures, a given quantity of energy will be able to power vastly more computation, perhaps 10 to the 30th power more, or more still, than it can at today's temperatures. An advanced civilization, aware of this, might rationally choose to hibernate, to power down, to wait, to wake later in a colder universe, and do very much more with what it has saved. If this is right, then most of the older civilizations are asleep. They are here, distributed through the galaxy, but they are not signaling, and they are not moving. They are waiting for the temperature to drop. There are, of course, other proposals. There is the berserker hypothesis, in which sterilizing machines, sent out long ago, wait quietly and destroy any civilization that reveals itself. There is the transcension hypothesis, in which advanced civilizations move inward rather than outward, into smaller, denser, faster substrates that we cannot see. There is the percolation model, in which colonization is a physical process with critical thresholds, and civilizations expand only in patches. And we happen to sit in an unoccupied patch. There is the possibility that we are simply first, that we arose too early in cosmic history to have any peers, and the older civilizations to whom we would eventually be an interesting neighbor do not yet exist. There is the possibility that we are wrong about what to look for, that the older civilizations do not use radio, do not send probes, and do not do anything we would recognize. There is the possibility, most simply, that they are exactly where we would expect them to be, and we have not yet listened long enough. And there is the possibility, the one that many working astronomers quietly consider most likely, that no one else exists, that the great filter is behind us, that the Earth is not an accident but is, so far as our galaxy is concerned, the accident, that we are alone. None of these proposals is provable. Several of them are not, in any near-term sense, testable. Some of them are essentially philosophical, but they represent the shape of the modern thinking about the silence, a shape that has grown over 60 years into a genuine field of scholarship. The paradox, in that sense, is no longer just a paradox. It is a subject. The question tonight is not whether we will ever answer Fermi. It is what we do while we wait. Since December of 2021, we have had, orbiting a point in space called the second Lagrange point of the Earth-Sun system, a telescope called the James Webb Space Telescope. It is the most sensitive infrared observatory ever built. Its primary mirror, folded during launch, is 6.5 meters across, nearly 3 times the collecting area of the Hubble Space Telescope. It sees, in infrared wavelengths, what the human eye cannot: the atmospheres of planets around other stars. For the first time in our species' history, we can, in principle, sample the air of another world. The Webb has done this now for several dozen exoplanets. It has looked at the atmospheres of hot Jupiters and warm sub-Neptunes, and a small number of rocky worlds close to their stars. It has found water vapor and carbon dioxide and methane, and, in one heavily contested case, a planet called K2-18b, a molecule called dimethyl sulfide, which on Earth is produced almost exclusively by marine microorganisms. The K2-18b detection has been argued about in the professional astronomical literature for the last 3 years. Independent reanalyses, published through 2025, have not been able to reproduce the finding to the level of confidence originally claimed. As of tonight, the presence of dimethyl sulfide in K2-18b's atmosphere is considered by most working exoplanet astronomers to be unconfirmed. It may be there. It may not. The Webb is not quite sensitive enough to be sure. But the fact that it is not quite sensitive enough that a slightly more sensitive telescope might be is the shape of the future. Later this year, in August of 2026, the American Space Agency will launch the Nancy Grace Roman Space Telescope. Its primary mirror is the same size as Hubble's, 2.4 meters, but it has a field of view 100 times larger. It will, among many other things, survey the galactic bulge with high enough sensitivity to detect around 1,400 new exoplanets, some as small as 1/10 the mass of Earth. It will fly a technology demonstration coronagraph, a device that blocks the light of a star so that the very faint light of a nearby planet becomes visible. That technology is the direct ancestor of the coronagraph that will fly on the next generation flagship, called the Habitable Worlds Observatory, targeted for launch in the early 2040s. The Habitable Worlds Observatory is a 6-meter space telescope whose specific mission is to directly image and to spectroscopically characterize at least 25 Earth-sized planets in the habitable zones of nearby stars. If any of those planets have atmospheres like ours, oxygen, methane, water vapor, ozone, the Habitable Worlds Observatory will, in principle, see them. And if any of them have atmospheres unlike ours in interesting ways, atmospheres out of chemical equilibrium in ways only life can produce, on Earth, the Habitable Worlds Observatory will, in principle, see that too. In the meantime, in June of 2025, in the Chilean Andes, a new observatory called the Vera Rubin Observatory saw its first light. Over the next 10 years, it will image every accessible part of the southern sky, every 3 nights, in 6 colors. It will produce, in that decade, more astronomical data than has been produced in the entire history of the discipline before it. It will catalogue interstellar objects passing through our solar system, transient events, the faint infrared excesses of stars around which vast engineered structures, Dyson spheres in the old thought experiment, might be hiding. And on the ground and in the sky, the radio arrays continue to listen. Breakthrough, Listen, enters its final years of its original 10-year commitment. The Allen Telescope Array, restored in 2024, is back on the sky. New instruments, the Meerkat Commensal Survey, and beyond it, the Square Kilometre Array, still being assembled in South Africa and Australia, will, in the coming decade, expand the hot tub in which we have been listening into something more like a small pond. None of this may be enough. It is possible that all of this listening, and all of this looking, and all of this planning of ever larger and ever more sensitive instruments will produce, over the coming century, exactly what the last 65 years have produced, which is silence. If that is what happens, we will have learned something. We will have learned that either there is no one, or that the ones who are there are quieter and stranger than any of our models. Either of those is a large thing to have learned. And if what we hear one afternoon is a signal, narrowband, from a direction we can name, at a frequency we recognize, that repeats when we look back at it, then something else, very much larger, will begin. For now, though, the sky above us is quiet. In 4.5 billion years, our own sun will become a red giant. In the same amount of time, the Milky Way and the Andromeda Galaxy, currently drifting toward each other at about 110 kilometers per second, will collide and merge and become a single, much larger elliptical galaxy that astronomers have already, half in jest, named Milkomeda. Any signal we send tonight will, by then, have traveled about 4.5 billion light-years. It will not have reached even the nearest of the great galaxy clusters beyond ours. Any reply from any civilization that has heard us is, if it exists, already on its way. It is somewhere in the great volume of space between us and its sender. It is traveling at the speed of light. It is arriving, invisibly, into the wave of information that continually washes across the earth from every direction, in every second. We are, in that sense, always listening. Whether or not we hear anything is a separate question. The reason the question matters, I think, the reason people have kept coming back to it since Fermi's lunch in New Mexico 3/4 of a century ago, is not that the answer is important. It is that the asking is important. It is a way of asking, in a form that a physicist can hold, what our place in the universe is, whether we are the only mind that has ever formed, whether we are one of many, whether the emptiness we see is the way things really are, or whether it is a stage set, or a mask, or a moment before the noise begins. There is no answer tonight. There may be no answer in our lifetimes. There may, in the end, be no answer at all. But the sky is quiet, and the listening continues. And the telescope, tonight, is being pointed at another star.